All right, so this is where we left off last time. So the the gravitation between the sun and the planets caused the planets to go in orbital motion around the sun. And by the way, that's what happens with the moon going around the Earth, right? You can think of the exact same thing. There's a force between the Earth and the moon, and that keeps the moon in orbit around the Earth. All right, so it's just basically if you think of it in terms of the moon, the and this is true for the planets as well. The moon is constantly falling towards the Earth, right? But it's not falling in the traditional sense, like, if you dropped a rock and it fell towards the Earth. What's happening with the moon is it's moving so fast that it's moving so fast, parallel to to a tangent line that's touching the orbit of the moon. So imagine this tangent line. It's moving fast enough that it keeps moving away. It keeps going around the Earth. All right, we'll see this in a little bit more detail shortly. All right, so gravity it turns out to be this universal idea that there's this force that is connecting all objects with every object with every other object. So it's actually tremendously complicated. We tend to simplify it in situations like this, where we say, her finger here represents the Earth, and this represents the moon, or this represents the sun, but it's not just the sun pulling on the planets. The other planets are pulling on each other, right? And the other stars out there. But the thing about the stars, and when we find out the actual equation for gravity, the stars are so far away that they have very, very, very almost no, well, to put it this way, no significant effect on the motion of our planets. It's really our sun that controls the motion of the planets in our solar system, because the sun is so much more massive than anything else in the solar system, and the mass is the thing that is really important in gravitation. All right, let's see. So gravity holds the stars together. As a matter of fact, that's how stars are formed. It's responsible, as I already mentioned, holding the Earth in its orbit around the sun, and the motion of our sun goes all the way around the Milky Way. It takes about 25 million years. I'm sorry, 250 million years. Sorry about that. To go all for the Earth, the Earth and the sun, to go all the way around the galaxy. And then there's this other, we're actually, our galaxy is part of this thing called the local group. And then it's, gravity is dictating the trajectory of our galaxy through the local group. And our local group is, it gets more and more complicated, is part of what's called the Virgo supercluster. We're actually part of this giant supercluster, and there's many superclusters out there in the universe. That's just our supercluster, which is different than the local group. The local group is just about a dozen or so galaxies that are gravitationally linked to each other. All right. Anyhow, so that's kind of beyond what Astronomy 101 is talking about. We're mostly interested in planets, all right? But it's perfectly fine to discuss galaxy of stars, and stars themselves and so forth. It turns out it wasn't really Newton that first proposed this, about gravity being being responsible. It was probably Galileo actually who first proposed it. Um, but what Newton does is he adds mathematical precision to these ideas that like no one had ever done before. I mean, when Newton's done with gravity, there's an equation that you can use. You just need some algebra, and actually just algebra 1 in high school is enough algebra to get through Newton's law of gravitation. All right, so that's we're going to deal with that today, or in this video series. So the moon's motion was explained. You often hear the talk about Newton and the moon, and that apple falling on his head and all that. I mean, one of the great insights that Isaac Newton had. Or we can say so. That's a bunch of nonsense about an apple falling on his head. Okay, if you've ever heard that before or anything like that, let me just turn you away from that idea. But Newton's family actually did own an apple orchard. He was never interested in the family business. He was much more interested in the natural world. And so, just like Galileo before him, the motion of an apple falling from the tree. Well, I don't know if Galileo thought about that, but Newton certainly had seen some apples fall from some trees. But the thing that really makes it amazing is Newton says, "Hey, well, wait a second. That is what causes the moon to orbit the Earth, and not only that. I mean, it's not just he doesn't just say that. He actually works out the details, like with an equation that he discovered. All right, which we'll come to shortly. So orbital motion can be understood as projectile motion. Okay, so remember, projectile motion is like when you fire something into the air and it makes a curve through the air that is parallel to the Earth's surface, such that the speed is gravitationally deflected towards the surface and its offset. I mean, it's kind of hard to just with the words to understand that. It's kind of easier to see it. Okay, so this is much easier to talk about. Okay, so in fact, in Newton's book, it's what's called the Principia or Principia, however you want to pronounce it. A very famous book, a very influential book. In that, he actually draws a little picture of a cannon, and the cannon shooting a cannonball. And he realized that, hey, of course, people have known this for a while, that if you put more charge in the cannon, the ball will travel faster and it'll land further away. Okay, so that's anybody who it didn't take a genius like Newton to figure that out. But so this is the genius of Isaac Newton. He realizes that, hey, well, wait a second. There must be a velocity, right? So I can shoot the cannon can travel along. So and by the way, in this picture, he's not taking into account air resistance, right? Because, I mean, you have to get up above the atmosphere. Otherwise, the orbit gets degraded very, very quickly. All right. Anyhow, the idea is what's important. If you fire the cannonball with a certain velocity, it'll go a certain distance. Greater velocity, it'll go greater distance. And then there comes you reach a velocity where the cannonball leaves the cannon and never ever returns. It just keeps going around the Earth. And that he worked out, that's what's called the orbital velocity. Right? So that's and by the way, that's different than the escape velocity, as we're going to see. All right, so now let's get into. All right, so just keep that in mind. We'll return to orbital velocity and escape velocity, and we'll really concentrate more on escape velocity. I mean, it's almost the same equation. You, you just take out the square root of 2, and it becomes the orbital velocity. All right, so we'll return to that. All right, so now this is what I was thinking about earlier when I was talking about Newton's second law. Okay, so the second law says that that an object will continue in straight line motion. Just like the first law, right? It'll continue in straight line, uniform motion. Uniform just means it's the same, unless this is the first law that I'm talking about. Unless an outside force acts on it. Okay, so now what happens when there is an outside force, a net force, if you will? So like there can be multiple forces. I mean, car goes down the road. There's lots and lots of forces acting on it. As long as it stays at the same speed, the net force is zero, and so its inertia carries it along, right? Right. So what happens is when there's a net force, let's say you're driving down the road and the speed limit changes and you accelerate, you push the gas, and you want to get up to 65 miles per hour or 70 or something like that, right? So when that happens, right, there's a the engine provides a net force on the axle and on the tires, and the tires provide that net force onto the road, and so the car accelerates down the road. So accelerating is either moving. It's really just changing velocity. That's acceleration. So whether you could be driving down the road and just traveling at the same velocity, and as soon as you hit the brakes, all right. So let me go over this. By the way, this is really important, right? I like to use a car because people are generally pretty familiar with driving a car. So there's actually 3 ways to accelerate. All right. So one is the obvious. You hit the gas, right? So you're driving down the road and you push down harder on the gas, and the car accelerates, right? That's the normal thing that's actually called positive acceleration. Or you're coming and there's a light, there's a red light, and so you hit the brake. That's also acceleration, but we call that negative acceleration. In physics and astronomy, we generally just talk about negative acceleration. Nobody uses the term deceleration, right? So we just stick with acceleration, and negative or positive, right? And then the third and final way, okay, so step on the gas, step on the brake, or you turn the wheel, right? The moment you turn the car, that you are actually accelerating. You don't have to change. The speed doesn't have to change, but the velocity changes. The velocity is a combination of the speed, the speed that is registered on your speedometer. Let's say you're going 50 miles per hour. That's the speed. But as soon as you change directions, you're changing the velocity, and therefore you're undergoing acceleration. Right? So that's an important idea. All right, so there's acceleration right here. So going around a curve, even if it's the same. So this is the same speed, 10 meters per second, 10 meters per second. But as soon as you change directions, you're undergoing acceleration. So this is, of course, speeding up, right? 10, and then 20, and then 30 meters per second, right? So just turning in a curve, or going in a circle, or going in an ellipse, you're undergoing acceleration, right? And so there must be a force that is causing that. That's how the second law works. Mass. So mass is a strange quantity. It's kind of hard to nail down what mass is. It's the amount of matter. But another way of thinking about it, as they say right here, is it's the amount of inertia the object has. So the more mass of an object, the more difficult it